Good morning, good afternoon, and good evening, everyone. So today we're going to be continuing our lesson on functions of several variables, right? So here we're just going to do a little bit of exercises on some of the concepts we already learned before we dive into the other ideas. So last time what we did was, well, we described it verbally, what it means to have a function of two variables, and we gave two examples here, such as finding the temperature given a longitude x and latitude y. So this is a function of two variables, right? If we plug in an x and y, then we get a certain temperature at a place on Earth or a point on Earth. And similarly, when we're finding the volume, well, we need a radius and a height. So we can plug in a radius and a height to find the volume of a circular cylinder. Yeah, and we were able to define things here. And we said that the input has two variables, x and y, and these are what we call the independent variables, while its output, z, which we'll call z, is a dependent variable. And we went ahead and did an example where we evaluated a function and we sketched its domain. And we did that twice. Okay, so let's go through some examples here. So here we're being asked to find and sketch the domain of the function and this function is f of two independent variables x and y is equal to the natural log of 4 minus x squared plus or minus 4y squared. Okay, so how do we find and sketch the domain of this function? Well, let's find the domain first, right? Well, the domain is basically when what's inside our natural log. So, right, the condition was say we're given ln of a, then we say that a should be greater than 0, right? So here we just say that when we're given whatever this input is, well, we say that it should be greater than 0. Right? And from here we can isolate some stuff. I guess we can put 4 in one side maybe. We can do that. So here we get this, which is greater than -4. So here I'm just solving the inequality. I could get rid of or I divide everything by -1, basically. So I get rid of my negative, but then that changes my sign. And there we go. There's actually an ellipse. So this is some ellipse. And we're saying that, okay, that's my rule, basically. So if you write it in formal notation, well, we can say, okay, let me put this here. So we can say that my domain is a set in which I have these 2 points, and my rule is that, well, this thing has to be less than 4. That's the only rule I have. Okay, that's the formal way of writing it, or at least from the textbook. And then from here we can Now we can draw. So now we sketch. So how do I do this? Well, okay, let me just do that. And then, well, my domain is this, right? So x squared plus 4y squared is less than 4. It's probably some ellipse. Not sure how it should look like. Uh, maybe like, okay, but this is just a guess. And it's also less than 4, so meaning it should be inside that thing. So, and also here, look, we're scaling the y. And since we're scaling that y, it's probably like, I don't know, something like this, maybe, right? Should be something like that. Yeah. And then it should be, my domain should be everything that's in here. I think. Yeah, should give us a similar. Just checking. Oh, is it 9 minus, is that the thing that I got? It's kind of a similar example here. 9 minus x squared. Okay. Then how do they solve that thing? What? Oh. Oh, and then after he did this. Okay, he wasn't done yet. Okay, my bad. So after that, it should have been 1/4 x squared. I divide everything by 4. So now that's my domain, right? And then I sketch. So here I'm scaling this thing. Yeah, I forgot. The equation of the ellipse should have like a radius of 1. That's why I have to. Oops. Something like this. Something like that. Because here I'm scaling my x. Yeah. Okay, then okay. So that's done. Okay. Ooh, we have like 49 here. Okay, we do it again. Um, so here I find and sketch domain of function. Yeah, I forgot. So just a note for me. When we're dealing with an ellipse, it has a formula, and I think it was because an ellipse is in 2D. Or no, not the area of an ellipse, an equation of an ellipse. So yeah, it's this. Oh, okay. So x squared over a squared plus y squared over b squared. This is something I actually tend to forget because yeah, just something that I don't often use. Ellipse, hyperbolas, And then when you get into their 3D, yeah, it's just something I don't often use. Here though, we assume the center is origin. So my center is at 0, 0. So that's not the most general formula. Yeah, the most general formula is when you add, so this becomes x minus h, and this becomes y minus k, where h and k are the center, right? That's the most general formula. But in this case, I'm fine with that. Yeah. Okay, let's move on. So we do the same thing. So my, what do you call this? My function here is as follows. F of x and y. Here we're given square roots. So we have 9 minus x squared. I subtract that to 25 minus y squared. And from there, I find my domain, right? What can I say? Well, both of these should not be negative, right? So my domain is the rule such that when I'm given these 2 points, the rule is that my 9 minus x squared should be greater than or equal to 0, as well as my 25 minus y squared should also be greater than or equal to 0. So those two have to be equal to 0. Now, how do I simplify? Okay, let me simplify on my own. Oh, I can just switch these. So I get x squared less than or equal to 9. And from the other one, the other condition that we have, you can say my y squared is less than or equal to 25. So there. Those are my two conditions. Now, how does that? Okay, now my issue is how do I look at that? Or how do I solve for that inequality? Let me see. Yeah, because here I get a line in one of our examples. The other one I get parabola. Here I get an ellipse. Here I get a number or a solution of some sort. Um, so yeah, that's something. I guess I can do this, but that's plus and minus 3, and this one is y plus and minus 5. So if it's a plus, it's gonna stay this way. But if it's a negative, it's probably gonna go the other way. So what's gonna happen is that this is going to be less than or equal to 3, but greater than or equal to negative 3, right? And then the other one, so this is going to be y is less than or equal to 5, but then y is greater than or equal to negative 5. So something like that. So I have like 3 conditions here. Um, Let me see if I did that correctly. I'm not super sure. Also, oh yeah, I'm also not sure if it's a circle or a square, but I think it's gonna be a circle, judging by the way how it looks. And so it should be greater than or equal to 0. Oh, and then we have oh, so it is a square. Okay. So the idea was I could actually combine these things. So I could say -3 is less than or equal to x less than or equal to 3. Then the other one I could say -5 is less than or equal to y less than or equal to 5. So now I have these two inequalities, right? Let me copy. There. That's the solution. That's the domain. And now I sketch it. So when I sketch this thing in 2D, I can see, oh, well, it should be a 5 here and a -5 because that's my restriction. Here it's a -3 and a +3. So should be something like this, right? So this is my entire domain, right? So something in between for my y value, I forgot to add that. So here we say we're in the xy plane. Our y value is in between -5 and 5 inclusive, as well as our x is in between -3 and 3 inclusive. So yeah, let me see if we get that. Oh, that's funny. Because there's one with the dotted lines and there's one without. Okay. Oh, without it means not including, I think. Without it means it's not including. Yeah, it's not including. But this one's including. So that's also one thing. So we have to see if it's including. Okay. It's a good thing they looked up on that. So this one's including. Okay. And then we do it again. Uh, oh, where'd that go? Okay. So here, uh, what's happening? Oh, I can't erase. So here again, I do it. Uh, I'm given a function. I find its domain. And then, yeah. Okay. So here we have square root of y minus x squared over 9 minus x squared. So what's the condition? Well, the condition of my domain, so the rule given 2 points, is that my y minus x squared should be greater than or equal to 0. And my 9 minus x squared should not be 0, right? Or else it's going to be undefined. What else can I say? Yeah, that's it. That's all I can say about it. So now let's simplify these conditions. So when I see this, I immediately see, oh, my x squared is less than or equal to y. So here we actually see a parabola. And my other condition was this, which is not equal to 0. Well, I see that my x squared should not be equal to 9. And so that means my x should not be equal to uh, positive and negative 3. Yeah, so those are the two conditions that I have. So if I rewrite it again, there we go. And now I sketch my domain. So here I see my XY plane. Let's try the first. Actually, we'll do this one, the second condition, because that one's easy. That one is just, well, if we have, let's say, a negative 3 here, we have a positive 3 here. Well, we know it's not going to be in one of those lines. So not in those lines, right? What else can we say? We have a parabola, and so it's going to be going up here. I don't know where that intersects. It probably does. It intersects when, of course, x is negative 3 and x is 3. And I get some y value, but then we don't include that. Um, and here we're saying it's less than or equal. And so, like, where should it be actually? Yeah, I just realized, where in the world should this be? Uh, I think it should just be like what? Like up here. This is our domain. It's everything that's up here. Because we're saying that my x squared is less than or equal to y. So including this thing, as well as when it's less than. Uh, yeah. So it's probably like inside this function, kind of. That's how I think of it. Let me just double check. Okay, so he gets the domain. He says that this y is greater than or equal to x squared. Okay. He gets that x is equal to plus minus 1. So, but in my case, it's 3. He puts those conditions in. He draws a parabola. He draws two lines. Okay. Yeah, that makes sense. Okay. Yeah, that was it. Yeah. Okay. Um. Okay. Now we do another sketching of the what is this? Here we're being asked to sketch the graph, but really we're just evaluating. What? Okay. Here's what I'm gonna do. I'm gonna write it out, and I'm gonna take a screenshot of the table. So here we're being asked to find, oh no, not find, sketch the graph. But all I'm doing really is inputting points here. So let me just do that. So here I have f of x comma y. This is equal to x squared. And here I see, oh, I have a table. Let me just get my table. Here we go. So that's my table. Make it bigger maybe. Okay. And we're being asked to basically kind of evaluate all of these stuff, right? So here, like in this case here, what if I have f of -2, -3, right? So here this is f of -2, -3. Then -1, -3, and then so on and so forth. What's funny is that I don't have to do anything to y. That's what's funny. So whatever I get here, I also get down here. So I really don't know, like, anyways. So if I get -2 and -3, I plug in my -2, I get 4, right? Here I have a -1 and a -3. I plug it in, I get 1. 0, -3, I get 0. 1, -3, I get 1. 2, -3, I get 4. And then I basically get the same thing here, right? If I type it in, that's funny though. So, ooh, nice pattern. 4, 1, 0, 1, 4. Nice and easy. Then same goes at the bottom row. 4, 1, 0, 1, 4. So I just take every x value and I square it pretty much. That's all I did here. If I update my graph, oh, look at that. That looks really cool. Wait, let me actually take a screenshot of that graph. That looks really nice. So in my 3D space, I get something that looks a little bit like this. Yeah. So here's like this is really cool though. It's sort of a parabola. It's like a parabola. Yeah, and it has these points here, X, Y points. Pretty cool. So I think another advantage, or no, one thing that functions of two variables can do that single variables cannot do is graph functions in 3D. So that's one thing it can do. That's pretty cool. This is like a parabola. It's a bit funny though. It looks kind of boxed. But anyway, okay. Let me hit submit, see what happens. Yeah, these are one of those problems where it's just a free point pretty much. Okay. What do I do here? Okay. It's mostly like sketching. I'm good with that. Okay, these ones are a bit funny. So here it's now identifying the graph of each function. That's cool. And I'm supposed to guess which graph it is. Okay, now we have a contour map. So that one I have yet to look at. Okay. More contour maps, contour maps, contour maps, contour maps. Oh, transformation of graphs. Okay. And yeah, that's it. So it's mostly just about graphing. They put a big emphasis on graphing, huh? That's interesting. Okay, so number 5, let me go ahead and do this. So here we're being asked to sketch the graph again. Sketch the graph. But in reality, we're not the one doing the sketching. Our homework is just telling us to plug things in algebraically. So let's do that. Okay. So here I have my f of x, y, my functions of two variables. And I'm, what is it? it's equal to 7 minus x squared minus y squared. And okay, so I have to ask, or I have to write an equation for the cross section at z equals -4. So here, basically, I just plug in everything. So I have to write an equation for its cross section when z equals -4 using x and y. So I don't know. When z equals -4, then my function is literally the same thing because I don't have a z here. It doesn't matter. Right? Or unless I'm messing something up. Uh, oh, my z is my f. Yeah, I totally forgot that. Yeah. So when my z is -4, well, this is -4. So here we actually forgot when again we're looking at 3D, we have to say, or we have to put some condition here that z is some value k that we don't know, right? So that's actually there, -4 equals my f of xy. I'm gonna quickly write that, see if I get it. If I don't, okay. Oh, I'm not writing anything. So -4 equals 7 minus x squared minus y squared. Let me see if I get that actually. Mm, yeah, I have a couple of tries. I just want to see if I get it. Okay, let me see. Um, okay, I got it. Yeah, so that's what it means. So here we just like plug in. Yeah. Okay. And then here we're also being asked when z is 0. So here we just plug in 0 instead. That's simple. Okay, let me just copy and paste that. And so I just replace this with a 0. Then when z is 4, so again, I copy and paste. I remove my 4. When y is 0, using x and z. Okay, let me do the others as well. I've just been copy and pasting it. When z is 4, well, I basically just have like what? 4 equals 7 minus x squared minus y squared. And then, okay, here's where it shifts a bit. It changes a bit. Here we're being asked when y is 0. What's x and z? So here we have z equals 7 minus x squared. Done. My y squared is a 0. Right? And when my x is now 0, when x is 0, here I have z equals 7 minus y squared. And we're done. So here we're just analyzing the cross sections when I try to input values for each of my coordinates, right? Yeah, we got a nice looking graph actually. Actually, let me show the graph. So let's say quadric surface, right? This thing is a quadric surface. To be specific, we can identify what this is using our previous lessons. The idea being, okay, if I take out my z, I get what do you call this? It's two negatives, so I can just divide that. Or no, I put my 7 to the other side, and I get a circle actually. So it's this one. So this one is that xy. This is the one that's looking for those circles there. And then when I take out my y, well, now I have a parabola, and it's specifically a concave down parabola from the xz plane. So it's talking about this one, right? And then I have another parabola when my x is 0. So that's in the yz plane. And so if I have two parabolas, and then I have a circle, well, I have a circular paraboloid. That's the name of the shape. Cool. Okay. So just a brief recap on quadric surfaces. Okay. Again, sketch the graph. So many sketching. Of the function. And I'm given this graph here. Oh, now I have to do it by myself. 9 minus 9x squared minus y squared. So here, what I would do, I won't really like sketch it. I would just identify what the shape is. That's what I would do. So this is, the z is here actually. There's a z there. Yeah, so we identify what the trace is. That's what I'm gonna do. And I just find the one that looks similar. So here I identify my traces. So when I take out my z, right? So here I have z equals square root 9 minus 9x squared minus y squared. Oh, I can actually square this thing. So I can say z squared is 9 minus 9x squared minus y squared. That way it looks cleaner. I don't want to deal with square roots. That's basically it. Now if I take out my z, boom, taken out. Oh, if I take out my z, I have 9x squared plus y squared equals 9. And I can just divide everything. So x squared over 9 plus, no, not that, I'm wrong. I meant x squared plus y squared over 9 plus, not plus, equals 1. So here I have an ellipse. That's all I need to know. I need to know what kind of shape it is. So it's either going to be three things. It's a parabola, a hyperbola, or an ellipse. An ellipse slash circle, depending if their numerical coefficients are equal. So in this case, when I take out my z in the xy plane, I have an ellipse, right? Now if I take out my x in the yz plane, what do I have? Oh, so here I can add my y squared. Z squared plus y squared is equal to 9. Well, circle. Well, uh, if I take out my y squared, oh, I have an ellipse again. So my x is e plane. Circular ellipsoid is that thing. But yeah, so I have an ellipse, I have a circle, I have an ellipse. If I were to kind of draw like a prototype, so this is just an example. Briefly, how it would kind of look like. In my XY plane, I have an ellipse. So crap, I forgot what it looks like. Depends on where it was stretched, because we also have to take that into account. If I take out my Z, oh, my Y was stretched. Yeah, so it was probably like something like this, maybe. If I go to my YZ plane, I have a circle. My YZ plane is this. It's just a regular circle. And then if I have an ellipse here, XZ plane, oh, it's also stretched. Yeah, it's also stretched right about at my Z, right? Oh crap. I like forgot what it looks like. There's like a circle there. That's an ellipse stretching that way. When I take out my Y, I have this, I add. So I'm scaling it to Z. So the Z is the one that's stretched here. So I get something like this. Something like that, maybe. So if I were to graph it, oh my God, everything looks identical. Yo, everything's identical. What? That's interesting. Uh, what? What's the difference? Oh my goodness, I don't see a difference. They're all going to three. What? Bro, they all look the same. This is madness. I don't know. Can you see a difference maybe? Oh crap, I don't see any. They all look the same. What? That's funny. Okay. Uh, or maybe if I put them in a direction. Because, oh my goodness, they all look the same. C, X, Y. I'll put them here. Nah, they really all look the same. I'm not even kidding. In my homework right now, they all look the same. Oh, okay. No, so one's what? X, Y. Oh my goodness. Okay, okay, two of them are the other way around. Um, they all look the same. Oh, so here it depends on where I'm rotating it. Okay. God, what is that? That's really weird. It's the same thing I did. Oh, so what he did instead of trace identifying the traces, he turned everything into an yo. That's fun. Oh, so I have to find the x-intercept, the y-intercept, and the z-intercept of this whole shape. That's not fun. Okay, let's that's fun. Okay, let me actually do that real quick. Maybe there's something we can gain from doing that. So let me find intercepts. I think that's also a piece of information we can get. So if I make my z equals 0, or no, if I want to get my x-intercept, then I have to make my y and my z to be 0, right? And so I have 9, uh, So I have 0, 9 minus 9x squared minus 0. It doesn't matter. Okay. So I have x squared equals 1. And then if so I have 2x intercepts plus minus 1. So that means I have 2 points here. I have 1, 0, 0, and negative 1, 0, 0, right? If I want to find my y-intercept, then here's where I make my x and my z to be 0. So my y, okay, I have 0 equals 9 minus y squared. So I have y squared equals 9. And then I have 3 plus minus 3. So I have 0, 3, 0. And I have 0, negative 3, 0. And lastly, when I get my z-intercept, I get my x and my y to be 0. And so that would just be z squared equals 9, right? And so I have z is equal to plus minus 3. This would be 0, 0, 3, 0, 0, negative 3. And there. That's it, I guess. We can now find. Oh, I can't even look at it. Okay, let me see. So my z should have an intercept of 3, and I have that for all shapes. Okay. My y-intercept, 3 and negative 3 ideally. I don't know why it's not like. God, what am I looking at? 'Cause I have really, really. Mm. Oh yeah. Also another thing. Okay, got the intercepts. Oh, another reason why we don't include this, because z is supposed to be greater than or equal to 0, right from here. So we have a z squared, that's why. Okay. Uh, God, what am I looking at? Okay, let me just check. I don't know. I'll check the first graph. I cannot see. Negative 1. What? Negative 1 and 1 for my x coordinate. For my y, negative 3 and 3 for my z. Well, this one looks promising, so I'm just gonna hit this maybe. Use the description, right? Oh, there we go. It intersects the x-axis, negative 1 and 1, y-axis, negative 3 and 3, z-axis at 0, 0, 3. Okay, so it has a, I'm just gonna look at the description, because this one's wrong. Intersects the y-axis. Oh, okay. So it's scaling. So this one's wrong. My other one, the x-axis at negative 3 and 3. Is that the one we got? No. So it's not this. And then my last one, God, they all look the same. Negative 9. Yeah, so it's the first one, yeah. But they all look the same though. It's just the scaling. That's crazy. Okay, let me hit submit, see what happens. Oh, we got it. Nice. That was still crazy. That wasn't, yeah. What? Match the function with its graph. Okay, now we're matching. So again, I have to do that same idea, right? And I have to do it for like what, 7 times? And then here we proceed to contour maps. Yeah, it's not loading. These look really fun though. I mean, I would say the graphs are very visually appealing in my opinion, but some look the same, so that's also another thing. Anyways, yeah, so I'm gonna stop here. Um, yeah, so it's usually just about like labeling. But yeah, I hope you guys enjoyed, learned something. Personally, I was appealed by the art because I'm gonna admit the art was really cool. It's not really solving; it's just making a graph. I mean, yeah, we're probably solving to get the graph, but these look visually appealing. I just hope they have some applications though. Um, but yeah, I hope you guys enjoyed, and I'll see you all in the next one.